The Earth is a remarkable piece of real estate, and a busy one at that. From ever-changing weather patterns to the hustle and bustle of city streets, our planet is in a constant state of motion. However, if we take a look just below the surface, we find that things are always moving below our feet as well. It's called plate tectonics, and it's how the continents were formed and reformed and reformed. But before we get to that, let's dive underground to learn what our planet looks like from the inside out. Our Earth is made up of layers, and there are two types of layers we need to learn about in order to understand plate tectonics: the compositional or chemical layers and the mechanical layers. We could spend an entire session on what makes both of these types of layers unique, but for this lesson we're simply going to provide an overview. There are three primary compositional layers to the Earth's surface, and these are probably the ones you're most familiar with: the crust, the mantle, and the core. It's important to understand that the compositional layers refer to the materials or elements the Earth is made of. However, if we take a look at how the inside of the Earth behaves, we can divide them even further into mechanical layers. Starting from the outside working in, the lithosphere is the outermost layer of the Earth, which contains the entire crust and the topmost layer of the mantle. The asthenosphere contains the same materials as the top layers of the mantle, but the pressure and the heat are increased. It's not exactly a liquid, but it does move like heated rock, so you could say it's somewhat fluid. The mesosphere is next. At this level, the pressure is really starting to build, which restricts the molecule's ability to move, thus making it very, very rigid. Past the mesosphere is the liquid outer core. Extremely high temperatures melt the metals contained in this layer into liquid form. Think flowing rivers of lava, and you'll have a pretty good idea of what the outer core is like. And finally, we reach the solid inner core. Just like the liquid outer core, the inner core has extremely high temperatures and is composed of mostly metals, which might lead you to ask, why isn't it liquid as well? The answer is pressure. There's so much pressure at this depth that even though the temperatures are beyond the melting points of the metals contained in the inner core, the high pressure essentially squishes everything down into a solid. Now that we know a bit more about the composition of the Earth, let's move on to plate tectonics. Let's start with the history. In the early 1900s, a scientist named Alfred Wegener noticed that the coastlines of several continents looked like they fit together, similar to puzzle pieces. He believed that around 200 million years ago, all of the continents were joined together in one large supercontinent that he called Pangaea, which is Greek for all the Earth. Over the course of millions of years, Pangaea broke apart into the continents we know today, a process he called continental drift. Although his theories explained quite a bit about the origins of the Earth, scientists at the time weren't exactly impressed and initially dismissed his ideas. Fast forward to today, and Wegener's concepts are the basis of the modern-day plate tectonics theory. So what exactly is the plate tectonics theory? Well, it states that the Earth's outer mechanical layer, the lithosphere, is divided into large continent-sized plates that are constantly moving. How fast are they moving? Pretty slowly, actually. Around 1 to 2 inches per year, which is why it was so hard for scientists 100 years ago to wrap their heads around the idea. So what changed their minds? Well, a few natural discoveries in the 20th century made Wegener's theories seem more plausible. For example, in the 1950s and 60s, scientists discovered heated magma rising up through cracks in the oceanic crust called dikes, which is how new rock or new land is created. This realization that our planet is always reforming and reshaping itself from beneath lent credibility to Wegener's theories. Point Wegener. Not long after, scientists started plotting the location of earthquakes and volcanoes around the world and observed that the location of those events followed a similar pattern to the outline of the plates Wegener proposed. And then there was the fossil evidence. Fossils of tropical animal and plant species have been found in Africa and other places on Earth that are less than tropical. One plausible explanation was that Africa was once part of a larger continent that was home to these tropical plants and animals. Remember Pangaea? So in light of all this evidence, the scientific community started thinking maybe this Wegener fellow was actually onto something, which led to the development of our modern-day plate tectonics theory. So now that we know the history, let's dive a bit deeper into how it all works. According to the plate tectonics theory, these massive lithospheric plates are all moving in different ways, and how they interact with one another can have a huge impact on the Earth. Where these plates meet are called boundaries, and there are three kinds. Convergent boundaries occur when two plates are moving towards one another. Transform boundaries occur when two plates are sliding past one another, and divergent boundaries occur when two plates are moving away from one another. Let's take a closer look at what happens at each of these boundaries. As we said, convergent boundaries are when plates are moving towards one another. When the two plates collide, a couple of things can happen. One of the plates will dive under the other plate. It's usually the heavier, denser crust that dives under the lighter crust. This creates what is called a subduction zone. And the deeper under the Earth's surface that plate goes, the more pressure it creates. That pressure, coupled with a high heat, causes the crust to melt, forming magma. The magma presses up towards the surface, and voila, you've got a volcano. An example of this is the Ring of Fire, which is an active ring of volcanoes that encircles the Pacific Ocean. The other thing that can happen when two plates press into one another at a convergent boundary is the rock above the boundary will be lifted up or folded and form mountains. Ever hear of the Himalayas? That's an example of two tectonic plates colliding. And because the plates continue to move, the peaks in this mountain range continue to grow. For example, Mount Everest, which currently measures around 29,000 feet, grows around an inch every year. So as you could imagine, it takes thousands of years for these mountains to form. But although movement at convergent boundaries is usually gradual, as pressure underground builds, the impact above ground can be quick and violent. Fast movement or slipping of the land can result in earthquakes either above ground or under the ocean. And convergent boundaries aren't the only type of boundary that can result in earthquakes. At transform boundaries, the Earth's plates are sliding past each other in opposite directions, which creates a crack or fault in the Earth's crust. As the plates try to move, they rub against one another, resulting in the building up of pressure. If the plates are stuck for a long period of time, the pressure will continue to build at the fault line until eventually it releases, resulting in an earthquake. The San Andreas Fault System is one of the largest transform boundaries in the world, which is why that area has more than its fair share of seismic activity. That just leaves divergent boundaries. Like we mentioned before, divergent boundaries occur when plates are moving away from one another. Either the space between the two plates widens and becomes a large crack or rift, such as the East African Great Rift Valley that runs from Lebanon to Mozambique, or if the space between the two plates is under the ocean, where the crust is thinner, magma oozes up from the Earth's mantle and fills the space. This is called seafloor spreading. The Mid-Atlantic Ridge is an example of where seafloor spreading has occurred. The crust under the ocean pulled apart, allowing magma to fill the space between, creating the tallest and longest mountain chain in the world. So in review, the plate tectonics theory is based on concepts first proposed by Alfred Wegener in the early 20th century. It states that the Earth's outer mechanical layer, the lithosphere, is divided into large continent-sized plates that are always moving, leading many scientists to believe the continents we know today were once part of a supercontinent called Pangaea. These plates move 1 to 2 inches per year. Where they meet is called boundaries, and there are 3 different types. Convergent boundaries, where plates collide, transform boundaries, where plates slide past one another, and divergent boundaries, where they move apart. Volcanoes and mountains form at convergent boundaries. Earthquakes and tsunamis can occur at both convergent and transform boundaries. Fissures and large cracks in the surface occur when two plates move apart at a divergent boundary. And seafloor spreading occurs at divergent boundaries located at the ocean floor. So that completes our lesson on plate tectonics. As always, feel free to use the scrubbing bar at the bottom to go back and revisit any portion of this lesson.